Hi everyone, my name is Shuo from Lilienthal University. Today I will present our work, High-Fidelity SLAM using Gaussian Splatting with Rendering-Guided Densification and Regularized Optimization. With RGBD inputs, our methods run the mapping and tracking, namely a SLAM pipeline, to create a 3D Gaussian Splatting scene. Our method can produce sharper and cleaner map than previous neural-based SLAM and concurrent Gaussian splatting SLAMs. We first begin with the basic knowledge with the 3D Gaussian splatting published on SIGGRAPH in 2023. Different from the neural radiance field, which uses either a continuous or discrete volume to represent the scenes. The Gaussian splatting using some ellipses as primitives to represent scenes. When rendering an image, these 3D Gaussians will be projected to two-dimensional image plane as two-dimensional Gaussians. When rendering a pixel, a rasterization pipeline will be adopted and render pixel value, including the color, the depth, or even the feature. For a classical 3D Gaussian splatting scenes reconstruction, we need to prepare some images and then run the camera pose estimation. For example, the CoMap or any other structure from motion pipeline. Or when knowing the camera intrinsics, we can even first run some visual SLAM pipelines and then use the achieved camera poses for reconstruction. At last, we run the 3D Gaussian training. It's a kind of offline reconstruction. In some cases, like in robotics, we sometimes need an online reconstruction. An online reconstruction can help the scenes reconstruct better. For example, we can check and rescan scenes or the model for a better reconstruction quality. From a SLAM perspective, we want to explore how 3D Gaussians can be used in the mapping and tracking process. For our method, we found two problems when using the 3D Gaussians in the online mapping, which motivates our method. The first problem is we found the densification used in the original 3D Gaussian splatting is not efficient for an online mapping process. Second, we observed the forgetting problem during the mapping. Based on these two observations in this work, compared to other existing Gaussian splatting SLAM, we have two main contributions. First, we propose to expand the map from the rendering loss directly, which can effectively improve the rendering quality. Second, to alleviate the forgetting problem in such a continuous learning problem, we propose a regularization optimization to alleviate the forgetting. First, let's recall how the traditional visual SLAM create and expands the map. Commonly, new points are detected when new frames are received, and then triangulation is conducted to optimize new points in the map. For the 3D Gaussian splatting representation of the scenes is represented by a group of Gaussians. More importantly, here we not only care about the odometry trajectory alone, we also need to evaluate the map quality by the view synthesis. For example, when the camera moves to a new pose, we render the view at current camera pose. Then we compare with the live camera input, that is the ground truth image here. We compare the rendering loss to densify the map, which can help expand the unobserved areas and refine the quality of previously visited areas. During the mapping, we also observe the problem of forgetting for such an online learning problem. So what is the forgetting problem here? For example, the green Gaussians here are observed by the camera 0 at this pose. Then, when the camera moves to another pose, these red Gaussians are observed by camera 1 now. Note that these yellow Gaussians are both observed by the camera 0 and camera 1. However, with optimizing these Gaussians, They tend to be optimized to overfit the lattice frame, that is the camera 1. So here I show an example of keep tracking the first frame in the replica dataset. The yellow square here shows the shared Gaussians during the mapping. But after the camera moves, these observed Gaussians in the first frame will be optimized to fit the subsequent observed frames, thus resulting in the lower quality for the first frame rendering. So previously, a heavy replay buffer is often adopted, which means previous frames will be saved and replayed periodically, which will result in much memory consumption, and also each replay will consume a lot of time. So instead, we propose to optimize Gaussian parameters with regularization terms. Here, the origin parameters are importance weights, which are evaluated by parameter gradients in each optimization iteration. The larger weights means the Gaussians are not stable and tend to move to fit the current frame. This regularization term will prevent this kind of movement and change. Also, combined with our rendering-based densification, we can densify these unstable areas and avoid the dramatic change to Gaussian parameters. For the tracking, we track the camera pose by evaluating the synthetic view compared to the input. Tracking by comparing the synthetic view is not a fully new idea. In some previous direct visual SLAM methods, we minimize such the photometric loss for the camera pose estimation. However, in the past, we do not have such good quality of synthetic new views. The neural rendering for the tracking was first proposed by INERF in IROS 2021, which optimized the camera pose by minimizing the loss between the rendering image and the reference. The gradients of the rendering loss will be back propagated to the camera pose until convergence. In our method, we adopt the similar idea. In addition, since our inputs are RGBD, we also combine with the depth image. Namely, the tracking aims to minimize the rendering color and depth image with respect to the inputs. For experiments, we first combine with the baselines on synthetic dataset replica. Our method achieves the best rendering quality and minimum trajectory error. On the real dataset 2RGBD, our method achieves best rendering quality. However, note that our method does not perform well on the real dataset in the tracking. Qualitatively, compared to the neural rendering method, our method produces sharper rendering. And compared to some other Gaussian splatting SLAM method, our results is cleaner thanks to the regularized optimization. Here we show that combined with our densification strategy and regularized optimization, our method can produce better quality map. We do ablation study on our proposed methods. With our proposed strategy, the mapping quality and the tracking performance are both improved. At last, we talk about some limitations of current method, not only for hours. First, the running time. Our method can not be said to be real time now, though the Gaussian rendering is fast, above 100 frames per second. In a SLAM pipeline, the time consumed on the mapping and tracking cannot achieve real-time performance compared to some traditional visual SLAM. Second, the nerve and Gaussian splatting SLAM is based on the assumption of multi-view consistency, which might not be reliable in a real dataset due to the camera overexposure or the motion blur. At last, currently the nerve of the Gaussian splatting SLAM cannot be applied to the large scale scenes directly due to the GPU memory consumption. At last, we summarize our work. First, the running loss-based densification can help create the map efficiently. Second, the regularized optimization can help alleviate the forgetting problem without consuming much extra time.